All right, guys, thank you everybody for coming. I'm Trey Grainger. I'm our Director of Engineering of our search group at CareerBuilder. Our technology headquarters is just up the street. We're over in Norcross, so not too far from here, maybe a 20-minute drive. But I'm here today to talk with you about scaling recommendations, semantic search, and data analytics with Solr. Those are a lot of topics, so I won't go super deep into any of them, but I'll definitely try to cover as much as I can. Before I get started, how many of you guys actually use Solr today? Just to get a feel. Okay, so about half of you, and the rest of you guys are new. You just want to learn about technology, see what's capable of. Yep. Okay, good to know. So I'll get started. So just give you a little bit of background about myself. I have been at CareerBuilder since 2007. I joined there as a software engineer. Got my MBA from Georgia Tech in Management of Technology at the end of 2012. Went to Furman University for undergrad, studied computer science and various other things. And I most recently authored a book on Solr earlier this year. You guys may have heard of it. It's called Solr in Action. You guys can, just got a copy here if you want to see. It's a
great book.
Thanks, Pritesh. So,
use it anytime.
One of our audience members suggests it. Highly recommends it. And then just some fun stuff outside of here. I've spoken at Lucene Solr Revolution a few times. It's coming up in about a month. Less than that, a couple of weeks. Yeah. So it's a really good Lucene Solr conference if you guys want to learn more about the technology. Also, I'm the founder of a gluten-free search engine called Silly Access. If any of you guys have to eat gluten-free or know someone who does, it's a good resource. And then my whole team at CareerBuilder, lots of us are open source contributors, mostly to Lucene and Solr. So I'll show in a little bit some of the work we've done to move Solr along in the data analytics space. So general overview for what we're going to cover today. First of all, we're going to talk about our search infrastructure, and I've got my manager of our search framework here, Joe Shrieky, who's going to be talking about some of that for part of the talk. I'm going to talk about how we use Solr as a recommendation engine at CareerBuilder and ways that you can do the same. I'm going to talk about semantic search and some of the things we've done with Solr to try to move beyond pure text searching and really trying to understand the meaning of what people are searching for and make the search results better. Finally, I'll talk about data analytics and then have some Q&A at the end if you guys want to talk through some things in more detail. So just to give you a feel for CareerBuilder and what we do there, Solr is one of the most critical technologies that we use. We've got Hadoop, we've got lots of other capabilities, but Solr underlies a significant portion, probably 90+% of all the products that we have at CareerBuilder. So to give you a feel for the kinds of things that Solr is used for, we've got job search. If you guys are familiar with us, you've probably seen our job search capabilities for job seekers. Resume search. The autocomplete capabilities all across our site are powered by Solr. Job recommendations. Resume recommendations. We've got a supply and demand portal that takes market supply. So supply would be candidates looking for jobs, and demand would be the jobs where companies are looking for candidates. And we crunch that data across the entire employment industry, and we show trends. So you can search for particular keywords, skills, any combination of information you want to find, and zone in on where you can find people, how easy or hard it is to hire, the compensation ranges, market demographics, whether they have military experience, really any facet you could imagine wanting to drill down into, we provide that information back about the employment market. We have searching for companies. Again, this is the compensation portal I was telling you about. We're currently crawling the web to pull in social information for job seekers, whether it's from in the technology industry, maybe it's GitHub or Stack Exchange, Stack Overflow. We'll look at some of our competitors. We pull in any information we can and try to make it searchable so that recruiters can find people with marketable skills. We do various other forms of analytics on information coming in. Obviously, we've got lots of mobile presences, and this is maybe half of the different ways that we use search at CareerBuilder with Solr. This is my team. This is an outing we took earlier. Some of you guys may recognize this is over at Stone Mountain. Every year they have Snow Mountain where they blow snow, and so we took a team outing there to brave the non-Atlanta weather. These are a few of the folks. In terms of how my team is structured, there's 5 teams underneath me. There's our search infrastructure team and core search team. The search infrastructure team focuses on scaling Solr, so they handle deploying Solr to servers, our continuous integration environment, the platform and framework to move data around, so they support Cassandra, RabbitMQ, various other technologies to move data around across the cloud and multiple data centers that we have. And they support hundreds of servers, and Joe will talk about that in a few minutes. Our core search team is the team that focuses mostly on working with Solr directly. So this is the team that's in the Solr code. They're committing patches back to Jira for Solr. They're really building out new features and capabilities based on Solr that we can use in our products at CareerBuilder. And then we've got 3 other teams. A job search team, you can imagine what they do. A candidate search team, you can imagine what they do. And then a relevancy and recommendations team. And the relevancy and recommendations team is really focused on trying to understand the relevancy algorithms in Solr, building our recommendation engine on top of Solr, and using various other technologies like Hadoop to apply signals back in that we can use in the search engine to make search results better, to power semantic search, and then to build recommendations. So the first part of our presentation we're going to talk about as we go through all these different facets is we're just going to go in order through the things in the title is how we scale Solr. So I want to invite up Joe Streaky. He's our manager for our search framework, and he'll talk about how we scale Solr.
How's it going, everybody? A little bit about me. I got my Bachelor's of Science at Georgia Tech. No other interesting things like Trey that are super pertinent to the talk. So CareerBuilder has 2 million jobs, but we have and 60 million searchable resumes. We have about 450 distributed servers across, I think it's 7 now, different data centers across both the United States and internationally. We have thousands of uniquely, dynamically generated indexes. We allow our customers to kind of decide on the fly what they want their indexes to look like. And Solr has a great capability for having kind of dynamic indexes, whatever you need. We have 1.5 billion total search documents across all of our indexes, and we get somewhere between 2 to 3 million searches an hour across our entire platform. So that's kind of the level that we work at. So our search infrastructure for feeding, so we kind of get data from both SQL Server and Hadoop. SQL Server provides a lot of kind of location intelligence and some other extracted data about our users, and we use SQL Server as kind of our generic storage engine. It goes into a feeding stack. Today it's powered by Ruby written on top of Sinatra, and it reaches out to Cassandra to store the documents and RabbitMQ to queue the documents for processing. We have a monolithic processing architecture that allows us to do kind of generic batch processing, and that generic batch processing reaches out to RabbitMQ to see if there's any documents and then works them. We go through several different Rabbit transformation stages. So, for example, Solr really likes to be batch fed as opposed to individually document fed, and so one of our steps is we batch documents together before we send them off. And then we send them out to kind of multiple clusters in Solr. The reason we ended up with Cassandra as this storage vehicle is it scales kind of linearly with you add an extra machine, you get a little bit more space. We were kind of at the point where we had a $1 million SAN, and your only option after a $1 million SAN is a $2 million SAN. And we weren't particularly interested in that level of investment, whereas we could replace it with $500,000 of commodity hardware. Even though they all have SSDs, they're still not as expensive as the $2 million SAN option. And also provides really great reliability due to the clustering it allows. We ended up with RabbitMQ because when we were looking, it was the only queuing architecture that provided high availability, it provided clustering among the nodes. And we're really big on high availability. And if you're going to do queuing, you should use a queuing architecture. It handles a lot of the complexity for you. Don't do it yourself. It's a terrible idea. We did it. It was a terrible idea then. It's a terrible idea now. Today, if we rework this architecture, we'd probably look at replacing RabbitMQ with Apollo or with Kafka, as they're kind of a little bit more directly applicable. But Rabbit was the only person with clustering when we looked. We built this platform about 2 years ago, totally. So one of the ways we get our high availability out of Solr is we have multiple Solr clusters. Every one of our indexes is stored on at least 2 Solr clusters in our platform, so that if we need to take one down for maintenance, there's still a resource. If one crashes mistakenly, it's still a resource. We feed them both independently, so we can shut one down, do maintenance on it, start it back up, it catches up with all the documents, and off it goes. We have a dashboard visualization tool, which shows all of our servers. So this is one of our data centers, the one actually in Swanee. And so we have each of the little dots is an individual server, so we have quite a few servers. And this all allows us to have a generic API. And so we kind of, the core search team provides this generic API, and it allows all of our internal customers to search on whatever they want. They don't need to worry about all the complexity of getting documents into Solr, the complexities of building schemas, the complexity of all the fun stuff. We provide them the easy capability to add a document, delete a document, and search for documents. We provide an easy interface for facets, and we provide lots of support around, hey, how do you use this entire thing? So that allows a lot of our internal customers to very easily be like, hey, I want to search on this new kind of document, off they go. They just come talk to us, we flip a couple toggles internally, give them a machine, off they go. So it's a pretty great platform. Yes?
I'm assuming for the flexibility of the kind of data that comes in, that's the kind of data that goes to that Hadoop side versus the SQL side, or do you guys transform that into a structure?
So actually, most of our customer data just lives in Cassandra.
Oh, okay.
So a lot of so we have some internal data that lives in like SQL and lives in Hadoop, and then we have most of our customer data we just store in Cassandra, and then they keep a copy wherever they choose to keep it. Our kind of only single copy is in Cassandra.
Thank you.
All right, so moving on from scaling, I'm going to talk about recommendations. So there's a couple of talks that I've given at Lucene Solr Revolution before. I gave one specifically on building a recommendation engine with Solr. I'm not going to go as deep here, but I'm going to give you guys a general overview, and then if you want to learn more, you can go into the other one. Similarly with semantic search and with data analytics, I've given some talks on that before as well. So I'm going to give you guys a general overview of all the stuff we do and take questions, and there's some other resources out there you can check on. So recommendations, it may be obvious, but for a lot of companies, recommendations are as important or even more important than search. For CareerBuilder, we tend to measure the success of the company on the consumer side based upon how many job applications we can deliver to companies. So the more people we get on the site, the better, because we get more applications to jobs. And the better we can match with our recommendation engine or our search engine, the right person to the right job at the right time, the more successful we are as a company. We get more applications, more people get jobs. That's what fuels us. That's what makes us successful. With recommendations, I won't give you the exact number, but I will tell you that over half of all the applications that come through CareerBuilder, where people are applying to jobs, come through recommendations, not direct search. You can see similar numbers that are published from folks like, well, obviously you've got Netflix, where recommendations are key to everything they do, but you can also search there. I would say a lot of our competitors, you see the same thing. So the ability to take information you know about somebody and automatically drive content to them that is a good match for them without them having to do anything is very critical for a lot of businesses, especially web businesses, because people may come to your site one time, maybe you get their email address and they never come back, but if you can send them an email with relevant content, then they're going to come back time and time again. So I'm just going to walk you through an example of somebody who might come to CareerBuilder and the kind of information we have about them. So you might have John, who lives in Boston, is planning to move to New York, but he's really happy to move to any big city. He just wants to be in a city. He's currently a sales manager, but wants to move into business development. We might be able to find this information through signals. They might have a user profile, but this is the kind of information we could find out about somebody. Irene might be a bartender in Dublin. She wants jobs within 10 kilometers of her location, and she works in the food service industry. Irfan's a software engineer in Atlanta. He's interested in software engineering jobs, and he wants to work at a big data company. You get this idea, these personas, this information you can collect about somebody. And then this last one I have here is Jane, who's a nurse educator in Boston, seeking between $40,000 and $60,000 working in the state of Massachusetts. Somewhere in the state, probably she would prefer Boston. So we have this information, and we have Solr, we have jobs with this kind of information. What can we do with that? What we can do is we can take Jane and turn her into a query. In this case, Jane, automatically, we run a query against Solr, and we say, I want to search for the job title of nurse educator. If it's an exact match, I want to boost it high. If it's not an exact match, it's okay. I also want to match it, but just score it lower. And also, I really want to find somebody in Boston, or find a job in Boston for Jane. But if it's not in Boston, at least find one somewhere in Massachusetts. And by the way, she does have some salary stipulations. She might be willing to go a little bit lower. I'm sure she'd be willing to go a little bit higher. But let's add a piece to the relevancy calculation that boosts jobs up that meet her salary requirements. And so this is actually an example that I put in Solr in Action. The data for it, the jobs you come along with the book, and you can go on GitHub and download them. But when I put those jobs in the search engine and run that query for Jane, these are the kinds of jobs that come back from Solr. So this first one, remember, Jane was a nurse educator in Boston, seeking between 40 and 60K, working in the state of Massachusetts. So the first one that comes back is a clinical educator in Boston with a $41,000 salary. It met every single one of the requirements. It got the highest relevancy because of the way we constructed the query. The next one, I've got a very limited data set that I'm working with, but the next one is also a nurse educator. It's also in Massachusetts, in a city which I think is close to Boston, though I don't know the geography, so don't hold me to that. And it's also in the salary range. The next one, nurse educator, also Massachusetts. It's not in Boston. It doesn't meet the salary, but it's the next best match that I had in my data set. So you get the idea. Now, Jane could have come to our site and typed all this stuff in herself manually, but if we can collect that profile information about her, there's no reason we can't automate a query for her and generate good matches. And so in doing that automated query, what have we done? We've built a recommendation engine. And there's many kinds of recommendation engines. Just to give you my definition of a recommendation engine, I would say it's a system that uses known information or derived information from that known information to automatically suggest relevant content. And so in our example, where we had Jane and a bunch of attributes about her, that's an attribute-based recommendation. And I'll show you in a few minutes some behavioral-based recommendations using a technique called collaborative filtering, which you're probably familiar with if you've dealt with recommendations. If not, I'll explain it to you. So before I do that, I want to talk about what a search engine is. So I don't like, this is the blurb you'll get if you go on the Lucene page about what Lucene is. And they say Lucene is a high-performance, full-featured text search engine library. I prefer to change that a little bit. I like to say that Lucene is a high-performance, fully featured, token matching and scoring library which can perform full-text search. So even though it can do full-text search, that doesn't mean it's the only thing it can do. In reality, as you saw, we were searching on salary numbers, we were searching on locations, we were searching on all sorts of different attributes. Text just happens to be one of them. And if you really want to take it to a more academic level and go into the machine learning space, you could say Lucene is a multi-dimensional sparse matrix with very fast and powerful lookup and vector multiplication capabilities. If you know linear algebra or are familiar with recommendations, that will make sense to you. And I'm going to walk you through an example in a second. But you can think of each field as a matrix containing each term mapped to each document. And so as an example, when you take a search engine, for those of you who aren't familiar with Solr, the way a search engine works at a basic level is it takes documents. Those documents might have an ID, and then they've got some text, a content field in the document. So I've just got some made-up documents here. Document 1, once upon a time in a land far, far away. Document 2, the cow jumped over the moon. What the search engine does is it takes all of the individual contents from each of these documents, or every token is mapped to the documents in which it appears. And this is called an inverted index. And so what happens is whenever you go to run a search against the inverted index, you look up the keywords you're searching for, and you immediately have an answer of every document that those keywords appear in. So take this as an example. I'm searching for the keyword software engineer. This is the inverted index inside of Lucene. when I run the search, you see engineer is mapped to all the documents it appears in, software is mapped to all the documents it appears in. To run the search software engineer, I don't have to go through every single document and analyze the text in real time. All I have to do is look up in this index the keyword software, find all the documents it appears in, look up the keyword engineer, find all the documents it appears in, and then take the intersection of those two sets, and I get all the documents that software engineer appears in. So that's the basics of how a search engine works and how Lucene/Solr work as well. But it doesn't have to be just text. It could be any attribute. So if you think of Lucene and Solr as a matching engine, they can match text. They're good at matching text. But anything you put into the search engine could be matched. It could be text, attributes, locations, results of functions. You can do math calculations on the fly. User behavior, the classification of the user or the person running the query. If you can put it in the search engine, you can search on it and match on it. So to do recommendations with Solr, these are a couple of different methods you can follow. There's attribute-based, like I showed you with the example for Jane. There's also classification-based. So I could take all of our jobs and I could classify them into a hierarchy of categories. For example, for us, it might be medical, nursing, oncology, and you kind of dive deep into those. And when you run the search, you can take the person and their classifications, maybe a couple of different ones with different confidences, and you can search jobs with different confidences, and the matching takes place, and then the scoring takes place on top of that matching to deliver you really relevant results. You can also do text similarity-based recommendations. So there's a capability in Solr called the more like this handler. I'll show you an example of how to use it in a bit, but if you don't have any information other than the text content, it's a way to do text-based recommendations. You can also do concept-based recommendations. So if you know that a software engineer is related to Java and search, or sorry, the Solr is related to software engineer, Java, search, and open source. When someone searches for Solr, instead of just looking for the text, SOLR, you could search for these related concepts as well and generate really good recommendations there. There's also collaborative filtering, which is the typical, think of the Amazon model. Users who purchase this product also purchase these other products. You can apply that same behavior in Solr by indexing the behavior of your users and how they interact with your content. I'll show you that momentarily. So collaborative filtering. The way you can implement this, let's say that you don't have any knowledge about your users other than the content on your site that they've interacted with. In our case, they might search for jobs, they might click on jobs, they might apply to jobs. So what can we do? We can take every document. In our case, let's take an e-commerce example here. A user who bought a product. So document 1 represents a product, and then every user who bought the product, user 1, user 4, user 5, we can reflow that document to Solr and stamp on that document all the users who purchased the product. That's the original document. It becomes this inverted index of which we talked about before, which is an index of every user mapped to every document that they took an action on. When we want to do recommendations for that user, what we can do is look at all the documents. I'm going to flip the scenario and talk about CareerBuilder. I'm going to look at all the documents that are jobs that they've applied to. So I've got a user who applied to document 1 and document 4. What I can do is run a search for document 1, document 4, find the users who applied to those documents, and turn those users into a query. So once I get the top users back who applied to those documents, applied to those jobs, I can then turn around and take those users, create a query against my job search engine for those users with weights. The caret 2 says apply a higher relevancy weight. I can search for those weights for those users on the jobs, runs that query against the search engine, and generates a list of documents, in our case jobs, which match the behavior. My apologies.
Nothing to apologize for.
You did that intentionally.
So I can run a search for the users who previously applied to those jobs, and what I get back at the end of the day is recommendations for other jobs that are like the jobs like those users, which are like the jobs that they applied to. And this doesn't you notice this doesn't have anything to do with text. There's no information about the user whatsoever. This is all based purely on the behavior of the user on your site, and you can generate recommendations for similar content based purely upon the behavior of other users. And I'll tell you, having done recommendations for many years, that across the industry, collaborative filtering is the best way to do recommendations. If you look at companies across the industry, almost every single time you'll see that collaborative filtering beats out any kind of content-based or attribute-based recommendation capability. Not because there's some theoretical reason it has to, it's just that you're crowdsourcing the intelligence behind how you're doing your matching across all of your users, and they're telling you which documents are related, which is much better than you're going to be able to do with an algorithm you write yourself. Today. Maybe in 10 years that won't be the case, but that's how the industry is today. So that's using behavior to do recommendations with Solr. I mentioned earlier the more like this capability in Solr. And what this is the ability to start with a keyword query and find a document, and then find similar documents based upon text similarity. Or to start with a blob of text, send it to Solr, and have Solr score that text and tell you what other documents are related by having similar textual features. So I'm not going to go into the details of how the query is constructed, but in this case, I'm sending a query to Solr for the search J2EE, and I'm asking it to find me all of the documents that are most closely related from a textual basis to the top document matching this query. And so this is also, again, with Solr in action, you can download the code and run these examples yourself. But in this case, for my J2EE search, these are the top documents that came back. The reason they came back is because Solr said that J2EE, Java, senior developer source code, that those words were significant in my starting document, and those are the words that it searched for in other documents. You'll notice that there's a lot of noise in there too. I didn't filter out any stock words intentionally to show the example. You see and, to, a, for, of, really words that you wouldn't want to include in your recommendation approach. It so happens Solr is really good at not counting these very high based upon the way it does its relevancy calculation, using term frequency inverse document frequency calculation. So at the end of the day, you get really good results, but you can see that the source data it's using to do the match is maybe not the best. Another example where instead of running a search, I actually take a full document and pass it in. In this case, I just grabbed a blurb about Solr from the Solr homepage, passed it to the search engine, searching for jobs, and said, hey, find me jobs that match this description textually. And the ones that come back are Enterprise Search Architect, Senior Java Developer, and Java Lucene Software Engineer. So you see the results that come back are really good, and the underlying reason for that is that the top scoring text within that document compared to the rest of your content was search, Solr. Really those two words alone are the ones that boiled these to the top, and then you've got some other noise words in there as well. So the outcome is very good. There's some noise under the covers. There's ways to improve it, but if all you have is some documents and text, and you want to take a document and match it to the text of other documents, you can use this out of the box with Solr without having any other domain knowledge or anything like that. So it's a good tool if that's your use case, to do recommendations without a lot of domain knowledge, just based on text. At CareerBuilder, we do a lot of other... Hey, you have a question? Yeah.
Sorry to interrupt, but you were going through the collaborative filtering before the content-based.
Yes.
Okay, so here, does it use the internal ranking, the Solr internal ranking, or you kind of had to do on top of your query to rank the items that you search?
In this particular example, it's just using the basic default similarity in Solr using TF-IDF.
Okay.
Yeah.
Can you change that?
You can. In Solr, it's in Lucene as well, but in Solr, there's pluggable similarities. So on a per field basis or per schema basis, you can change the similarity. There's several of them that are included by default with Lucene and Solr as they ship. What I'll tell you is you can play around with those similarities, and they matter in a lot of cases for text searching, but most of the value that you get, once you move beyond plain text searching, really comes from the data you use that you pass to the algorithms and not the underlying algorithm itself. In this case, I recently talked with one of the Hadoop committers, and he was describing to me the way that the Mahout algorithm works and how they're actually moving toward a model much more like this, where you pre-compute the data and you pass it into something like Solr and use Solr as the basis to do recommendations for a couple of reasons. One of the things that stood out to them that we realized years ago is that the TF-IDF scoring is actually really useful in the case of collaborative filtering, because you have a lot of people who are, let's call them noisy spammers, who act on every single document. And when you use the TF-IDF calculation to score, you actually penalize those folks and the people who only apply to a few jobs or only purchase a few products. Their vote basically counts higher. So it's actually, that algorithm in particular is really useful for this problem.
Yeah, we actually use TF-IDF in our collaborative filtering implementation, but we don't use Solr and Lucene. So
yeah.
I'm particularly interested why, whether we could just adopt the implementation from Solr. Maybe I'll ask you more questions about the difference between the two.
Sure.
But this is good. You can just use Solr by applying a query.
Yeah, and we actually tested Mahout a few years ago, and what we found is that this approach gave us significantly better quality results. I have a buddy who worked at a startup doing recommendations a few years back, and he was using Mahout, and he brought me in, and I was talking with him about what we did with Solr, and he switched over to using Solr, and I think the quality of the recommendations went up by 10 or 15% when they did that.
Do you mean speed or?
No, the actual matching quality.
Oh, really?
Yeah, and there's various reasons for that, and I will say that Mahout is currently in the process of completely migrating and transitioning the way they do recommendations, and it's probably going to be more comparable, maybe even better than this in the future, but that just for data reference purposes. So in addition to just this behavior and just these attributes, one thing that we do at CareerBuilder that's fairly interesting is mining of user behaviors to try to learn facts about users. For example, what we found in aggregate is that this is people's willingness to move for a job. If someone called them up and said, hey, we've got a job we want to offer you, would they be willing to move? And what we find is that at the 95th percentile, restaurant workers, bartenders, food service workers, that they're not willing to apply to a job more than 20 miles away from where they live, at the 95th percentile. 5 out of 100 will move further than 20 miles, will work somewhere more than 20 miles from their home. Versus software engineers, at the about 55th percentile, they're willing to move 500 miles away for the right job. So there's a lot of variance in people's willingness to move for the right job based upon the industry and the kind of work they do. It usually relates to the kind of income they're making, but not always. But these are the kinds of things that we can mine our data and learn in aggregate and then apply when we're running our algorithms. We can also do these kind of things on a micro scale on a per user basis, but based upon the data we have, sometimes that's a little more challenging. And then one thing I want to leave you guys with when talking about recommendations and search is this general notion that search and recommendations are on a continuum. So a lot of times people think about, I have my recommendation engine, and it provides automated recommendations. And I have my search engine, and you go to it and you put information in and let the user drive it. But in reality, if you think of a vehicle like Solr, where you put your text to search, and you also put your behavior and any other attributes, there's a lot you can do in the space in between on that continuum. For example, if somebody comes to your site and you know that they're a software engineer, but they run a blank keyword search in New York. They just type in New York. Does it make sense to show them random jobs in New York? Or should you push the ones having to do with software engineering up to the top? You can show them all jobs in New York, but you can modify the relevancy to show them things that they're more likely to be interested in. Similarly, if you've got someone who runs a search for nurse, and you can use their IP address to figure out that they're in Boston, why would you not show nursing jobs in Boston up closer to the top? Or if you've got a profile for them with other information, why would you not use that to try to give them the most relevant things within what they search for? The general idea is this notion between recommendations and search. You've got this whole personalization layer in between, where you can have it maybe be an augmented search, where someone types something in, but you also help them out. Google obviously does this. A lot of companies do this. But this is the kind of thinking you can undertake and the kinds of things you can build when you no longer view recommendations and search as two separate products and two separate technologies. So we talked about scaling Solr, recommendations, and now I want to talk to you a little bit about semantic search. So this is a general diagram of what we're trying to build at CareerBuilder. And the general notion here, you'll see at the top that I'm running a search for machine learning. And when I run that search, if you use Solr traditionally, you would search for machine and learning. And depending upon your stemmer or your lemmatization library, you might find a machinist who has learned something, which is not at all what you're trying to do. And so what we're doing at CareerBuilder is we're taking these text phrases that people search for and trying to understand the semantic relationship with everything else in our domain. So we look for related phrases, and when we mine our search logs and mine our content, we find things like data mining, MATLAB, data scientists, artificial intelligence, neural networks. We look for the most common titles from our taxonomy of job titles, and we see things like software engineer, data manager, data scientist, Hadoop engineer. Even though a Hadoop engineer may not necessarily know machine learning, there's probably a good chance that they're going to be familiar with it and there's going to be some kind of an overlap just based upon the domain. We look at occupations, we've got skills, we've got job levels, all sorts of information that's domain specific to us, but which we can find through mining our user behavior and our content and deriving these relationships. Then when we actually go to execute the search, instead of searching for a query which would find machinists who have learned something, we search for machine learning or at least two of the following: data mining, MATLAB, data scientists, artificial intelligence, neural networks, and then we can find everything that falls within one of our classifications and boost those to the top. We don't have to filter them out, but we can at least boost the relevancy up to the top if we know it's a good match. And that way the machinists might still be in there because it technically matches what you typed in, but they would be at the very bottom of the list and you'd probably never see them. Or if we really wanted to, we could filter them out. There's a couple of other ways. So we're doing a lot of machine learning. We're using Hadoop. We're mining a lot of stuff. That requires a lot of engineering and a lot of expertise, hiring people with PhDs in machine learning, in our case. If you want to have the sort of poor man's version of this and build something yourself, there are ways to do that with Solr out of the box. One of those ways is using the clustering component that's built into Solr. It's based upon an open source technology called Caret2. And the general idea here is if I search for something like .NET. So let's say, pretend like I'm an algorithm, I don't know what .NET is, never heard of it before, but I could search for it, find the things that are textually most related to it, boost those to the top, which is what the search engine is good for, and then I can start looking for links between those things. So when I search for .NET, many of the jobs listing .NET seem to be about software engineering. Some of them mention developer. There's this thing called a C#. I don't know what a C# is, but I think it's related to a .NET. Let me say music node, I'm not really sure, but the clustering says it's related. I've got .NET developer, you get the idea. So to set this up in Solr, again, I'm not going to walk through the syntax, but the slides will be available later if you want to play with this. You can set up the clustering component in Solr. You can then send a query to Solr. In this case, I'm searching for Solr or Lucene against job documents. And what the clustering component comes back with is a list of clusters, a list of terms and phrases that it identified that show up commonly in the documents which match that query. So you can see for Solr Lucene, I've got things over there like Java developer, architect, senior Java developer, Hadoop engineer, search development, those kind of things. I can then take those if I really want to, turn around and run those as part of my search, and generate something like this to augment or boost my original query. And then I'm no longer just matching the original text. I'm matching that text and boosting things up which match these other related things. So you could do that pretty easily out of the box without any sophisticated data scientists or machine learning folks in-house. You won't get as good of results, but it still works pretty well. And so for us, what we're currently in the process of doing is with our data scientists, we're investigating some methods for trying to understand the relationships between phrases in a more structured way. And so we combine a few statistical techniques. One is just using pure search co-occurrences. One is using a technique called point-wise mutual information. And then we're using a technique one of our data scientists is doing his thesis on, and it seems to work pretty well as well. The general strategy is I look at user search logs. So I've got John, he searched for Java developer in J2EE, maybe as separate searches. I've got Jane, she searched for registered nurse, then she came back and searched for RN, she came back and searched for nurse. Zeke, Java developer, Scala, JVM. We take the correlations across our millions of users, and by correlating those keywords together, we can generate lists of related phrases in the actual language that job seekers use to search for them, or that recruiters use to search for them. And that's very powerful because we can use those as suggestions, and we can use those to help augment the searches of users if they want to see other things they should be searching for. So here's some examples of the kinds of relationships that we find. So RN seems to be related to all of these other nurse-related keywords. Accounting seems to be related to accountant, accounts payable, finance, etc. And in this case, I took a few specific examples where we found some relations. And you can look at something like manager, where you could search for a manager, and it might be useful for you to know that other ways that that's represented are MGR, supervisor, director, lead, or leader. Those are other ways that people represent the word manager. In the case of a sales manager, you can see that people might type in sales, account executive, account manager, sales executive, sales professional, sales director, outside sales. Those are other common titles that people use. I had a conversation with Chris in the room earlier, I think, about that. So we're not just searching for the text sales, we're searching for these related things if we turn around and use this data for semantic search. You see for Hadoop, you get MapReduce and some other related technologies coming back as well. Some interesting things, which I won't spend time on, that we found as we've been doing this research are there's a lot of nuances with text. You've got a lot of synonyms where CPA means certified public accountant, RN means registered nurse. We've also got some ambiguous terms where someone might type driver and they mean a truck driver. Someone else might type driver and they mean an embedded systems driver. Typically we'll see these differences when we look at the recruiter side of our platform versus the job seeker side of our platform. But nevertheless, we're trying to make sure that when someone types one of these words in, if there's some other context, that we can guide it towards one meaning or the other. And then, of course, there's related terms, which aren't synonyms, but we know RN is related to nursing and Bachelor of Science in Nursing, and Hadoop is related to MapReduce, Hive, and Pig. They're not technically the same thing, but they're highly related. And so this is a mock-up of just to kind of show under the covers what we're able to do with semantic search at CareerBuilder. I took the example of Hadoop. And in our case, when I type in Hadoop, we can classify that to a normalized title of Hadoop DevOps Engineer, categorize it to these occupations, and then say, hey, these are the keywords that on average somebody would look at and say, these are the things that I would also want to search for when I search for Hadoop. Hadoop developer, MapReduce, Hive, HBase, Pig, big data. We have a continuum here, a spectrum, so if I want to get a little bit more lenient, I can extend it out and add some related technologies, OBIE, Lucene, Solr, Nutch. I can keep getting a little bit more aggressive, NoSQL, ETL, Java. You may not want to search for Java when you search for Hadoop, but we give users the option to expand it all the way out and see a lot of related things that are fuzzier, or keep it nice and tight and just expand to some related things. But it's this general notion of moving away from pure text search to what the meaning of the text is, and being able to augment the query based upon that.
Good.
Yeah.
Well, you talk about meaning, but it looks like you're really measuring statistical covariation.
Yep.
You know, we did some work with Cambridge Semantics where they actually try and map out the ontologies and try and work that out, and we could never get them to overlap. I'm just wondering, when you use the word semantic, does that mean the same thing? You know, it seems to me you're doing something a bit different than semantics.
Yeah, well, so for us, what we're not doing is we're not processing natural language as it comes in. Meaning I'm not allowing somebody to type, where can I find a Solr job, and parse that out and understand the linguistic variations. What we're doing is we're understanding the keywords people are typing in and what those keywords are related to. Really what other ways to represent them are, so that we can not just search for the text, but search for the other representations, but also search for other related things, kind of in a vector space model, search for other related things that would be more relevant. So it's all about relevancy. It's about getting the best matches to the top based upon matching multiple points of relatedness surrounding them. I think the definition of semantic search is something that everybody disagrees on and what it means. We don't have a we're not taking in pure natural language queries, so some people mean that by semantic search. For us, what we mean is when you type something in, we understand in our domain what that should be finding, and we find those things instead of just matching the text. So that's our version. That's what we mean by semantic search. And then the last topic I want to cover for a few minutes is data analytics. So everything I've talked about thus far has been focused on relevancy and matching and getting the right thing in front of the user. But one thing Solr is really good at is being able to run very, very fast searches for keywords or other pieces of information and bring back analytics. So in Solr, this is called faceting. But the general idea is I can build a product where I type in a keyword such as construction laborer, construction worker, and I can immediately see a breakdown of every document in my index and where it falls. So in this case, I've got top job posters, cities where it's easier or harder to recruit, what company they work for, most recent titles, the supply and demand of information. I can pull all of that out of indexes that have jobs and candidates. So why would we use Solr for analytics? There's a lot of big data platforms out there. There's a lot of analytics platforms. Well, for us, there's a couple of reasons. One is you can do ad hoc querying. So you don't have to pre-build any models to do analytics. You can literally type any keyword, a Boolean string, anything you want to type into Solr, match on the text, and then see what all the documents matching that text represent in terms of the facets and how they fall. Solr is also really good on the fly calculations. So when you combine facets and statistics and functions and grouping, you can do a lot of really cool on-the-fly things that you might have to pre-compute in a model otherwise. Solr is also horizontally scalable, so it can handle billions of documents, and you just keep adding more servers if you want to add more content, and you still get responses back to ad hoc queries on any piece of text or any other attribute in usually tens or hundreds of milliseconds. And they're insanely fast for the queries, so it really encourages user exploration. It's not generate a report, wait 10 seconds, get the report, see it. It's literally run a search, see the results, filter down on something else, immediately see the results. It's really good at being a discovery tool. So quick faceting overview. When you turn faceting on in Solr, there's a couple different kinds of facets. One is field facets. So in this case, if I facet on the field of city, I can see all of the cities that match my query with a breakdown of the count of documents within that city. We can also do query faceting. So in this case, I'm actually faceting on radiuses from a given point. So I can see that a count of all the documents that fall within 0 to 10 kilometers away from wherever my user was searching. I can see the ones between 10 and 25, 25 and 50, et cetera. So you can do basically a radius facet to see where the documents fall. I can also do range faceting, so if I have a numerical field, I can bucket the values together and see what falls within given ranges. This is the syntax you would use in Solr, if you're not familiar with it, to do those facets. If I turn around and visualize that data coming back from one of our products, you can do lots of things with it. Ultimately, the pie charts and the bar graphs are just taking a data point and showing the count, right? All of these are just facets. When we talk about supply and demand of information, this is supply, which is the total number of candidates falling within these locations for my given search. This is the demand for those candidates based upon the jobs posted within the same places. And then if we can look at labor pressure in our market by looking at supply over demand and seeing how easy or hard it is to hire and what the trend is over time in terms of easiness or ease or hardness of hiring. So those all look pretty, but go ahead.
Yeah, so a quick question. Are these all packaged queries that come with CareerBuilder? So if your HR person is using your product, they can pull these up naturally, or do they have to create their views?
No, these are actually standard views here. It's a supply and demand portal is what we call it. It's a product we sell, so you have to buy it. But it gives you full access to the labor market, and you can see employment trends. You can see where it's easier and harder to hire people. You can see compensation levels, what you should be paying people, what your competitors are paying people in some cases, if we've got the data.
So these are canned. You just buy the package and you get it.
Yep, you get it. And you can type in any query you want for any location, any keywords, any skills, all that kind of stuff. It's very much you drive it and you get the experience. So if you want to know how we did that, in terms of building that stuff. If you were going to build something like this with Solr, that first chart at the top, which is the trend over time, it's just the facet on the month. So I put a month field on my documents and do a facet on the month, and I can see all those documents plotted out over time. For the state map, I just did a facet on the state, got the counts back for every state, put them on a map. For military experience, same kind of thing. I faceted on the military experience field. Just basic facet queries with Solr, but when you put them in pretty pictures like this, they make people really excited. Same thing here. These are all just building blocks. I run a query for construction worker, facet on a location, and then you can see the breakdown of the top companies or the most recent job titles, whether they have management experience or not, what their experience ranges are. Again, all these things, we've indexed these values on the documents, and we just run the search and get the values back. This is an example of a radius facet. Like I was showing you guys earlier, you saw the syntax for it. Similar radius facet here. You can see facets on all these different locations. We've broken all the other data down here in little buckets. It obviously takes engineering time to model the data into Solr and to build these queries, but they're facets. I'm going to skip over this slide, but this is an example of how you can generate these radius facets and do it in Solr with Solr syntax.
I'm assuming everything you're showing us here was built against your CareerBuilder databases.
Yeah. Why do you ask?
I'm a sales guy, not an engineer, so I apologize to the room in advance.
Sure.
Is this the Cassandra database, the Hadoop, SQL, or a combination thereof?
So the data comes in. We've got jobs coming in from companies, and we've got resumes coming in from job seekers. Those go into SQL databases, and ultimately they get copied to lots of places. They go to Hadoop. We process them, turn them into search documents, and flow them to Cassandra, and ultimately to Solr. So the actual source of the data, let's just say it's CareerBuilder's data that we've acquired from job seekers and employers and various other places.
You guys do all the machinations and you push it into this Solr aggregation.
Yep.
Okay.
We put the documents into Solr, and then we use Solr as the vehicle to do real-time data analytics.
And then all you have to do is link these things to that Solr aggregation.
Yep, they're just queries that go in. The queries go in, we get the data out, we graph it, and we put a price tag on it and sell it.
I promise not to ask it.
Yeah, no problem.
So you mentioned that data,
Yeah.
the Solr data, when you push to Solr data, is it Cassandra supporting Solr?
Yeah, we use Cassandra as a cache in front of Solr, basically. If we want to upgrade Solr, we need to reindex the data to Solr, so it's nice to have the data in a place where Solr isn't our master source, or our only source of truth for the data. So it's purely just a cache in front of Solr so that we can reflow it into Solr when we need to. We use Cassandra, Joe was mentioning earlier, because it's really good at taking massive amounts of updates and reads, and it's easy to scale it by just adding more servers to it. So we can handle billions of transactions a day if we need to, whereas a SQL database would fall over. Our SQL databases have fallen over in the past when we've tried that.
So this is like normally you would maintain, serve all your reads with Solr, and then what usually you accumulate those updates with Cassandra, and then periodically update Solr. Is that a fair?
Well, we update live because a lot of our customers see a lot of value in that. But like that is certainly one approach you could take. Is you could batch up a batch of requests and then send them all up to Solr in a kind of a single batch, like how you want to feed daily or whatever. We do it kind of incrementally because lots of customers want us to do it incrementally. So there's a lot of interest in the company doing that.
Do you have anything based on just HDFS or HBase?
We don't currently build any of our Solr indexes offline and copy them in. All of our Solr indexes receive live updates. It's mostly the nature of the kinds of products we have and the kinds of updates that are coming in. We've got people 24/7 on our platform submitting jobs, uploading resumes, and we like to get the most up-to-date information out as quickly as possible. And in some cases, we do delay data going out, and we'll build it offline, but we don't build it in Hadoop. We probably will in the future for certain products. Today, everything streams in.
So do you see that it is a technical, is that recommended, is that a best practice for all the Solr implementations?
I think, so the question was, is it the best, for the camera, is it a best practice to always stream things into Solr instead of building the indexes, for example, in Hadoop offline? And the answer is no. It really depends upon your product. So if you've got a product where once a week or once a day or once a month you need to release data updates, and you've got the data in Hadoop, I would absolutely build the Solr indexes in Hadoop and then copy them out into your production servers whenever it makes sense to. But if you have the need to update the data in real time, whether it's the master record or some attributes associated with it, then you're going to want to stream that in to reduce the latency.
There's some overhead we pay for doing that kind of streaming, though. It's not, you don't get that for free, right? You have to, there's some extra architectural work you have to do to be able to do that kind of streaming.
I see. So, for example, if, well, I totally understand the benefits of doing live streaming, right? You get all the updates.
Yep.
Mm-hmm.
But if there's some model-based data, you have this is computed based on some very expensive model, you can't afford to run it every minute. So that will say updated daily, and then is it architecturally, I don't know. So is it good to how do we combine these kind of data which you can only afford to update daily? So you kind of just have to choose the live updates if you want to mix.
Well, it's like, I think it would matter if your documents are complete if they don't have this data that takes a long time to compute, right? So if you can have partial documents and like they still provide some value, you still might want to send them in incrementally. But if you kind of view like, hey, this document isn't complete until it has this pre-computed data attached to it, then you wouldn't want to put in the engine, right? Because it would immediately start coming back to customers unless you did some extra work to kind of hide it from customers, and that doesn't seem like it provides a lot of value for a bunch of complexity.
Yeah, I mean, you basically have three options, right? You build the model offline and you basically update all the data at one time. That's one option. You could do that in Hadoop, HDFS, however you want to do it. The other option is you stream the data in and keep the model separate and have to figure out some way to join the two. Or maybe you flow updates in without the model data on them and then you catch up later once you have the model built. What I've seen that works really well for a lot of companies is they have a model that gives them the best results, and they build that model offline as frequently as they can. But they have some intermediate model that isn't as good, but approximates what the original model would give them. So a lot of times, for example, if you build a model, say it's some machine learning model to a topic model or something like that, a lot of times you can host that model live and do some k-nearest neighbor algorithm to try to find the closest approximation to what the model would give you, and it's good enough for the live updates. And then as soon as you have your next batch of updating the model, you might get a little bit more precise answer, and you would just update the answer. I've seen that work really well. It requires a lot more engineering, but in a lot of cases, that'll give you the best result. Does that answer your question?
Yeah.
Okay.
Yeah. I was trying to think of what is the best scenario in my case.
Sure. One thing, quick plug, my team, Joe's team, have been working for the last probably 1.5 years, 2 years on getting distributed pivot fastening in Solr. If you don't know what pivot fastening is, I'll show you in a second. But when we talked about field fastening and all these kinds of analytics we can do earlier, it was on a single value. So it was, I want to see the city or I want to see the numerical value. What's really interesting in Solr is this notion of pivot fastening, which allows you to not just look at one value, but to look at, I want to see the state and the counts in the state, pivot that on each individual city, and then within each city, I want to pivot on some other information. So I'm excited to announce that this was recently committed to the most recent version of Solr, Solr 4.10, and I'm really proud of the team. The CareerBuilder team built most of this capability, and Chris Hofstetter at LucidWorks got it committed to Solr fairly recently. So the last example I want to go into is a combination of that capability, the distributed pivot facets, and stats within pivot faceting, which is a patch we've also worked on. It'll probably be deprecated and replaced with some better capabilities coming up. But the reason I mention it is because I want to show you, for all those charts and graphs I was showing you earlier with compensation and everything, what it's possible to do with the combination of these technologies in Solr. So in this case, I am asking to pivot on the state and then the city. I'm asking to then get numerical calculations for averages and percentiles for compensation for people who fall within those ranges. So if I'm searching on resumes or if I'm searching on jobs, what I can do is say within the state of California, this is the number of documents, and these are the percentiles of salary ranges that people fall within. And then if I drill down further into specific cities like Los Angeles or San Francisco, I can see how those break down and vary. And you could do this with a lot of queries to Solr for every single one of these values, but with pivot facets, you can send a single query to Solr and get an entire analytics dashboard painted for you with a single query, which is very powerful, and it saves a lot of computation time. So in this example, just to correlate the variables that go in to generate this data coming back, you can see the state, the city, the compensation, the percentiles. So to walk you through an example from what is an actual dashboard for us, I first facet on years of experience. You can see the number reporting there. That's just a basic field facet. I then do a stats pivot facet to get the average for the 16 to 20 years of experience. And you can see that graphed down here. For 16 to 20 years of experience, there's the average. I then do a stats pivot faceting with the percentiles capability built in. And I can see the breakdown of the 10th, 25th, 50th, 75th, and 90th percentile. And then, in addition to years of experience, I also want to show the metro areas people fall within. So everything we showed at the top, we do it down here, but instead of having to issue another query to Solr, it's just another pivot. So, and you can keep going with 10 or 20 of these. It will get slower the more you add, but it's still much better to do one query to Solr to paint the entire analytics dashboard with all the statistical calculations than to have to send hundreds of queries to Solr, which we actually used to do before we built this capability out. Yeah.
Do the documents that are actually returned in this index, are they?
It breaks them apart and tokenizes them into individual words or tokens, and then it indexes those tokens. So think of the search engine as a giant hash table where every keyword or every token is mapped to the documents in which it appears. And this is called an inverted index. And so what happens is whenever you go to run a search against the inverted index, you look up the keywords you're searching for, and you immediately have an answer of every document that those keywords appear in. So take this as an example. I'm searching for the keyword software engineer. This is the inverted index inside of Lucene. When I run the search, you see engineer is mapped to all the documents it appears in, software is mapped to all the documents it appears in. To run the search software engineer, I don't have to go through every single document and analyze the text in real time. All I have to do is look up in this index the keyword software, find all the documents it appears in, look up the keyword engineer, find all the documents it appears in, and then take the intersection of those two sets, and I get all the documents that software engineer appears in. So that's the basics of how a search engine works and how Lucene/Solr work as well. But it doesn't have to be just text. It could be any attribute. So if you think of Lucene and Solr as a matching engine, they can match text. They're good at matching text, but anything you put into the search engine could be matched. It could be text, attributes, locations, results of functions. You can do math calculations on the fly. User behavior, the classification of the user or the person running the query. If you can put it in the search engine, you can search on it and match on it. So to do recommendations with Solr, these are a couple of different methods you could follow. There's attribute-based, like I showed you with the example for Jane. There's also classification-based. So I could take all of our jobs and I could classify them into a hierarchy of categories. For example, for us, it might be medical, nursing, oncology, and you kind of dive deep into those. And when you run the search, you can take the person and their classifications, maybe a couple of different ones with different confidences, and you can search jobs with different confidences, and the matching takes place, and then the scoring takes place on top of that matching to deliver you really relevant results. You can also do text similarity-based recommendations. So there's a capability in Solr called the more like this handler. I'll show you an example of how to use it in a bit, but if you don't have any information other than the text content, it's a way to do text-based recommendations. You can also do concept-based recommendations. So if you know that a software engineer is related to Java and search, or sorry, the Solr is related to software engineer, Java, search, and open source. When someone searches for Solr, instead of just looking for the text SOLR, you could search for these related concepts as well and generate really good recommendations there. There's also collaborative filtering, which is the typical, think of the Amazon model. Users who purchase this product also purchase these other products. You can apply that same behavior in Solr by indexing the behavior of your users and how they interact with your content. I'll show you that. momentarily. So collaborative filtering. The way you can implement this, let's say that you don't have any knowledge about your users other than the content on your site that they've interacted with. In our case, they might search for jobs, they might click on jobs, they might apply to jobs. So what can we do? We can take every document. In our case, let's take an e-commerce example here. A user who bought a product. So document 1 represents a product, and then every user who bought the product, user 1, user 4, user 5, we can reflow that document to Solr and stamp on that document all the users who purchased the product. That's the original document. It becomes this inverted index of which we talked about before, which is an index of every user mapped to every document that they took an action on. When we want to do recommendations for that user, what we can do is look at all the documents. I'm going to flip the scenario and talk about CareerBuilder. I'm going to look at all the documents that are jobs that they've applied to. So I've got a user who applied to document 1 and document 4. What I can do is run a search for document 1, document 4, find the users who applied to those documents, and turn those users into a query. So once I get the top users back who applied to those documents, applied to those jobs, I can then turn around and take those users, create a query against my job search engine for those users with weights. The caret 2 says apply a higher relevancy weight. I can search for those weights for those users on the jobs, runs that query against the search engine, and generates a list of documents, in our case jobs, which match